Okay, so now before we start a new topic, uh, so remember that we finished off with Landau's diamagnetism, where we derived the diamagnetic susceptibility to be given by this formula. So before I jump into a new topic, I thought it's important for me to explain very explicitly how to shuttle between the microcanonical, canonical and grand canonical partition functions. So notice that in this course I have purposely focused on the microcanonical ensemble. That means I have always gravitated towards calculating entropy first. That is typically not what many other people, other authors and speakers do. They kind of, depending upon the situation, they directly use the canonical ensemble or the grand canonical ensemble. So I wanted to purposely not do that, because I wanted to emphasize the central role played by entropy in the subject of statistical mechanics. But it's also important to understand, in order to minimize the amount of effort you are going to put in practical calculations, how to start with the canonical ensemble directly if you wish to. So the way you do that is you start off, so recall that the entropy function, basically the number of microstates is exponential of the entropy, and that is given by just this combinatorial formula, which tells you is just the number of ways in which you can arrange your microstates such that the total energy, which is sigma I epsilon I n I, is constrained to be u, and also you constrain the number of particles to be n, but otherwise there is no constraint. Well, depends upon whether nature is described by, the particles in question are bosons or fermions or classical particles, but otherwise there is no further constraint. So, so this is how you count the number of microstates. So, it is a very combinatorial, discrete way of counting, and that is the essence of that goes to the heart of the notion of entropy, the fact that it is a combinatorial quantity. Now that we know what a combinatorial, how to define entropy from a combinatorial perspective, and so this is known as the microcanonical perspective. So it's possible to think of the canonical perspective, which if you recall that I had described the canonical ensemble by saying that you have a system where that system is allowed to exchange energy with the surroundings, which is a huge reservoir, and that is how I had defined canonical ensemble. They come to an equilibrium and the temperature equalizes. So it so happens that you can also think of it more mathematically. You can think of the canonical partition function more mathematically as the Laplace transform of the microcanonical partition function. So, this is the number of microstates, and you just multiply by e raised to minus beta u, and you sum over all the u's, and what you get is directly the canonical partition function. So you trade the energy for temperature. So basically you do a Laplace transform of the energy and basically you trade it for temperature. And again, so this would be a valid description of the canonical ensemble of the system. Now you can do a further Laplace transformation where you exchange the number of particles for a quantity known as chemical potential. So when you do that, when you do this further Laplace transform, what you end up doing is you get a quantity known as the grand canonical or the grand potential or the grand partition function specifically. So the grand partition function is easy to calculate, as you can see from this formula. There are no Kronecker deltas anymore, it is just a bunch of exponentials and they sum over all the n's. So you can expect this to be a simple geometric series for the most part, it is easy to calculate. So that is the reason why most people directly calculate the grand canonical partition function. They work with the grand canonical picture, and that's how we did it for the Fermi and Bose gases, if you recall. So we worked with chemical potential and temperature. That's because it's easy to do. Then for large systems, we have convinced ourselves that fluctuations are suppressed and the three are equivalent in the sense that they contain the same amount of information, and you can shuttle back and forth between the various pictures. All right, so now that's out of the way, let's get on with describing paramagnetism. So, if you recall, we stopped with Landau's diamagnetism, where the induced magnetic moment opposes the applied field. But here what happens is that there is no induced magnet, there is already a magnetic moment even before the field is applied. It is just that they do not all point in the same direction. So, in other words, every molecule has its own intrinsic magnetic moment, but they are all pointing in random directions. So, what a field does is basically it tries to align all the moments along the direction of the field. But then there is a competition to that from what is called temperature. So, basically there is a temperature which tries to randomize the spins, which tries to misalign the spins and make it isotropic. So, temperature tries to make the spins isotropic, whereas the magnetic field tries to align them, and there is a competition. So, the end result is some kind of a compromise between full alignment and full isotropy, and you get what is called Pauling paramagnetic susceptibility, which tells you how strong the magnetization is as a function of temperature and as a function of the applied field and so on. So, the goal is to calculate this Pauli's paramagnetic susceptibility. All right. So, in order to do this, I am going to start with an obvious starting point, which is that if you have molecules or atoms with intrinsic magnetic moment, so we are at liberty to denote it with a symbol called mu I, which is a vector for the ith atom. So, this ith atom experiences a magnetic field called H, and there is a energy that the magnetic moment interacts with the magnetic field, and there is an interaction energy of this form. So, the magnetic moment, as you very well know, is given by this formula, which is kind of easy to convince yourself of its validity. So, we know that the magnetic moment is basically proportional to the angular momentum of the suppose electrons in the outermost shell. So, the magnetic moment is going to be proportional to the angular momentum. So, the proportionality is going to be E over 2 m c. So, this is derived in various atomic physics or quantum mechanics courses. But then for spin, because the magnetic moment due to spin, basically spin itself is not as a result of something going round and round. So, it is not orbital. See, orbital angular momentum is because there is a charged particle going round and round, and if it is going round and round, you can actually derive this using classical arguments, and the magnetic moment comes out as E over 2 m c times the angular momentum. But then the spin is an intrinsic property of the electron, for example, which is not because it is going round and round anything. So, it is like charge and mass, it is intrinsic to the particle, and so special relativity gives this additional factor of 2, which is not explainable using Newtonian ideas, and you will have to just live with it. So, that is how it is. So, so the magnetic moment of an electron in an atom is given by this formula. It is E over 2 m c times orbital angular momentum plus twice the spin angular momentum. Now, because of quantum mechanics, you know that the square of the orbital angular momentum is, orbital quantum number is L into L plus 1, and the spin is being its half. So, it is 1/2 into 1/2 plus 1. So, now before we jump into the classical quantum picture rather, so this was the quantum description. Now, I am going to start with something simpler, which is the classical picture. So, now imagine there is a classical molecule with an intrinsic magnetic moment called Ji. So, rather E over 2 m c times J I is my intrinsic magnetic moment, and J is a classical vector. It is not a quantum object, not an operator, it is just a normal vector, and assume that the magnetic field is in the z direction. So, in which case the Hamiltonian, so I have to apologize for this being both the magnetic field and the Hamiltonian. So, I am going to put a subscript m there, signifying it's the magnetic field. This is the Hamiltonian. Okay, that's the magnetic field. Alright, so now notice that because J and Jz are all classical quantities, that basically and the magnetic field is in the z direction, the only component that is relevant is Jz, and Jz is J cos theta, where theta is the angle made by the magnetic moment with the z axis. Now, in order to calculate the grand partition, the canonical partition function, I will have to integrate over all the angles. So, the way to integrate over all the angles is this way. So, I am going to integrate over the angles by using this solid angle as the, so basically the density of states is 1 if you use the solid angle as your measure of integration, and this is how it works. So, this is how the canonical partition function is. This 2 pi is because of integration over the angle phi, and the integral over theta is from theta equals 0 to theta equals pi. So, just remember what that is. So, this is your theta, this is your phi, this is your x, y and z, and phi goes all the way from 0 to 2 pi, and theta goes from 0 to pi. Well, pi, like you will be covering an entire sphere. So, 0 to pi, so you will be going through a whole sphere. So, so that is what you are going to be integrating, and when you do that integration you get this answer. Now, you can go ahead and calculate the average magnetic moment. So, the average magnetic moment is so remember that if you want to calculate the average of anything, it is basically this one. H times whatever average you want to calculate divided by. So, this is the average of that whatever you wanted to calculate. So, the average of something is the phase space. So, you put the Boltzmann weight, it is called here, this is called the Boltzmann weight, and you multiply with the thing whose average you want to calculate, and then you divide by the total weight. So, that is what I have done here. So, this happens to be also equal to this, as you can easily verify, because so the log of so if I take the log of z and I differentiate with respect to beta, h means h magnetic. Okay, so this is the Hamiltonian, this is the magnetic moment, this is magnetic moment, magnetic field rather, not magnetic moment. So, this is magnetic field, magnetic field, magnetic field, magnetic field. Yeah, so if I differentiate with respect to magnetic field, take the log of z, differentiate with respect to magnetic field and multiply by temperature, which is 1 by beta, I get the average magnetization of the system. Okay, as you can easily convince yourself, because of this. Alright, so now because I know what z is now, I have just calculated it, I substitute that here and do the relevant differentiation, and I end up with this result, which tells me that the average magnetization is related to temperature and magnetic field in this fashion. and the magnetic susceptibility is basically defined as the linear. So, if I Taylor expand this in powers of h, so I will get something into h plus something into h squared plus dot dot dot. So, this something is called the linear magnetic susceptibility. So, so this is limit as h tends to 0, or the linear term, basically the linear term. So, there will be other terms there. Okay. So, there will be square terms. So, the linear term has this feature that it is inversely proportional to temperature, and the proportionality constant is this. So, this is called Curie's law. So, after Pierre Curie. So, it just basically tells you that the paramagnetic susceptibility falls off inversely with temperature. So, that is the linear paramagnetic susceptibility. So, now that was the classical description. So, if your magnetic moments were classical, that is how it is going to look like. But now the question is, what if the magnetic moments were quantum? So, remember that is how we started off. We started off this way, where we started off discussing electrons, but then we said let us do the classical case first, and we got this result, which is Curie's law. Now, let us go ahead and do the quantum case, where basically the electrons are now, because they have both orbital angular momentum and spin angular momentum, their states are now labeled by the total net angular momentum. So, which is L plus S. So, then you have both Jz and J, which is the quantum number corresponding to J squared, as being the good quantum numbers. Now, it so happens that you can kind of use what is called Wigner-Eckart theorem, which guarantees that L plus 2s is basically points in the direction of J, so long as you are interested in matrix elements between eigenstates of J squared and Jz. So, this proportionality constant is called Landé G factor, and this can be computed in the following sense, that you take the dot product with respect to J on both sides, and then you work out S dot J is this, L dot J is this, and L dot S, remember that L plus S is J. So, so basically J squared is L squared plus S squared plus 2 L dot S. So, and J squared is J into J plus 1, and L squared is L into L plus 1, and S squared is half into half plus 1, and that is basically your 2 L dot S. So, 2 L dot S is just a number. So, I am going to use that, and then I will derive this formula for the Landé G factor. So, the proportionality constant, it so happens that, see, the thing is that all my good quantum numbers are related to J. This L plus 2s is neither L nor S nor J. So, I want to be able to write it in terms of J. So, fortunately, Wigner-Eckart theorem allows me to do this, and it says that L plus 2s is guaranteed to point along J, so long as you are only interested in matrix elements with respect to the eigenstates of J squared and Jz. All right. So, and that proportionality is going to be this. So, this is called Landé G factor. So, I am going to use this Landé G factor, and then substitute instead of L plus 2s, I am going to write G into J vector. But then J vector dotted with H is basically Jz, which is m, the magnetic quantum number, the mj times h bar. So, that is the reason why there is an h bar here. So, it is E over 2 mc times h bar, which is already put into this. This becomes the Bohr magneton, and so I am going to have this mj here because it is jz. Then I will be forced to sum over all mj, and remember what the values of mj are restricted to be. They are restricted to go from minus j to plus j. So, I am going to be summing over all the values of mj from minus j to j, and then in order to facilitate this, I am going to make a redefinition of this quantity as x. So, when I do that, I can do the summation. This is just a simple geometric progression or geometric series, a finite geometric series, which you can do yourself. So, I get this answer in terms of this x. Now, as usual, I am going to go ahead and differentiate log z with respect to beta times the magnetic field, and I get my average magnetization in the z direction, and that is related to this function which is known as the Brillouin function. So, this is called the Brillouin function. So, now it is worthwhile to understand how this thing behaves for small and large values of x, because after all small values of x correspond to, on the one hand, small magnetic field, on the other hand large temperature. So, you can either look at small values of x as being because of large temperature or because of small magnetic field. So, that is the linear or classical regime. But then conversely, if x is very large, it could be either because the temperature is very small or your magnetic field is large. So, you can suspect that if the magnetic field is large, all the moments are going to be aligned. So, it is nice to know that that is synonymous with low temperature. So, that is telling you that when the temperature is low, also it is similar to the magnetic field being large. Alright, so let us work out the first case where the temperature is large or the magnetic field is small, in which case the average magnetization is going to be proportional to the applied magnetic field, and the proportionality constant is called the magnetic susceptibility. So, in this case this is paramagnetism. So, you have a susceptibility that is inversely proportional to temperature, and the proportionality constant is derivable in this fashion. So, however, at for low temperatures or high magnetic field, x is very large, and when x is very large, what is going to happen is that this cotangent hyperbolic basically becomes unity, because it's like cosine hyperbolic by sine hyperbolic, and they are both equal when the arguments are large, and then this becomes approximately 1 plus 1 over 2 j minus 1 over 2 j, which is 1. So, then when x is very large, this Brillouin function is 1, and because it is 1, the average magnetization is just independent of temperature at low temperatures, and it kind of saturates to the maximum value, which is given by the maximum magnetization that is possible when all the magnetic moments are aligned with the magnetic field. So, so that is the story of paramagnetism and Landau diamagnetism. So, the next topic we are going to discuss is what is known as ferromagnetism naturally, and the prototype or the simplest model that exhibits ferromagnetism is known as Ising model. So, I am going to first describe Ising model in one dimension, mainly because it is solvable exactly, but the downside unfortunately is that it does not exhibit ferromagnetism except at absolute 0. So, that is really puts a damper on things. So, fortunately things brighten up in higher dimensions, like 2-dimensional Ising model has non-trivial ferromagnetism at finite temperature, but of course, that is much harder to solve. So, let us see if I get around to it, I will discuss it, but I am certainly going to discuss 1-dimensional Ising model and some approximate methods to handle Ising model in 2 and 3 dimensions. Alright, so I am going to stop here, and in the next lecture I am going to discuss the Ising model.